A bus that supposedly comes every 10 minutes on average. So why, whenever I head out, do I always wait more than 5 minutes? It's not in your head, it's math. Today's story begins at a bus stop, with one small grievance. The sign reads, "This bus comes every 10 minutes on average. Just miss one and it's 10 minutes. Get lucky and it's 0, so on average it's half, about 5 minutes. Sounds reasonable, right? But once you're actually standing there, you always wait more than 5 minutes. It's not in your head, it was set that way from the very start." This phenomenon has a name, the inspection paradox, or, in its bus version, the waiting time paradox. Today we'll dig all the way to the bottom with no formulas, from buses to class sizes, families, and cancer screening. All the tools you need are addition and division, and the perspective of what you count by. A bus comes every 10 minutes on average, so you'd think you'd only wait 5 minutes on average. Where does that go wrong? This calculation hides an assumption that the bus arrives exactly every 10 minutes, like clockwork. If they ran like clockwork, the time left would spread evenly from 0 to 10 minutes, and the average would be exactly 5 minutes. Real buses aren't clocks. Thanks to traffic, signals, and passengers, they come bunched together or stay away for ages. The moment the gaps turn uneven, the tidy half the average calculation falls apart. Today's key: when you head out to the stop, you land at a random point on the time axis. Drop a point on the timeline and the long gaps are wider, so you land in a long gap more often. That's all there is to it. Let's take a very short slice out of a single bus line's day. The white bars are bus arrivals, and the numbers between them are the gaps. The narrow gap is 3 minutes, the wide one 21 minutes. And yet the average gap on this line is exactly 10 minutes. Each dot is a passenger who showed up at a random time, yet they cluster especially in the orange long gaps. The 21-minute gap is 7 times wider than the 3-minute gap, so there's 7 times as much room for a dot to land. Throw darts at random and they stick in the wide cells more often than the narrow ones. The average gap a passenger experiences is the mean of the gap squared over the mean of the gap. The chance a random passenger lands in a long gap is about 64%, well over half. Count the buses and the average is 10 minutes, but the gap a passenger experiences climbs to about 13.8 minutes. The gap you wait in isn't a random one. It's a gap drawn with a bias, so the longer it is, the more likely you land in it. This phenomenon, where bigger things get drawn in proportion to their size, is called length bias sampling. If buses ran clockwork-precise, the paradox would vanish as if it were never real, because the engine was never the average. The culprit isn't the mean, it's the variance. Let's look at 3 routes that all share the same 10-minute average gap. On the bunched route, 8 out of every 10 buses arrive packed 2 minutes apart, and now and then there's a gap of over 40 minutes. This picture is the engine of the paradox. On the left is the arrival timeline. On the right, the expected versus actual wait. Run the simulation and clockwork gives 5 minutes, random about 10 minutes, and bunched a whopping 18 minutes. The more uneven it gets, the longer the gaps that open up, and a random passenger gets pulled into one of those gaps, waiting out the whole interval. To be honest about it, waiting out the whole interval only holds for the most random bus of all, the Poisson case. If the gaps have mean mu and variance sigma squared, the average gap is mu plus sigma squared over mu. The average weight is exactly half of that, mu over 2 plus sigma squared over 2 mu. Since variance can never be negative, the passenger's gap can never be smaller than the timetable average. For a Poisson process, the variance equals the square of the mean, so the gap a passenger sees stretches to exactly double. On the Seattle Rapid ride that Jake Vanderplas analyzed, the wait ran longer than half the gap, but it never reached the full gap. This gap feels oddly familiar, doesn't it? The gap in the friendship paradox is also mu plus sigma squared over mu. Step away from buses and the same trap is waiting. The bigger something is, the more often it catches your eye. Out of 10 courses, 9 have 10 students each, and just 1 is a big lecture of 100. Count by course and the average is 19 students, worth advertising as small classes. Ask the students and 90 of them say 10, while 100 say 100. Count by student and the average is about 57. The big course is just overrepresented, the school didn't lie. Real university data, 2, 23.7 per course becomes 29.1 as students experience it. Households, 2, the average size is about 3.9, but the home an average person lives in has about 4.9. Friends are the same. The more popular you are, the more often you get picked, so your friends have more friends than you do. Buses, classes, households. The amount of inflation differs, but in all three the direction is upward. Buses inflate by 100%, classes by 23%, and households by 26%. All three share one formula because we count not by the unit itself, but through what's inside it. Buses are the star here, so why call it the inspection paradox? Its birthplace wasn't the bus stop. The real starting point was the factory, not the bus stop. A part caught by inspection lasts longer than average. The longer lasting a part is, the longer it stays in service, so it's more likely to get caught by an inspection. It's exactly the same as the long gap paradox at the bus stop. It's the same reason the bulb that's on when you walk into the house tends to be an unusually long-lived one. This phenomenon was pinned down in renewal theory, which deals with processes of repeated failure and replacement. The nickname waiting time paradox was cemented by Feller in 1966, and inspection paradox by Cox in 1962. Inspection paradox, waiting time paradox, length bias sampling, the names differ, but they all point to one thing. Let's see where this paradox hides in the real world, and how not to be fooled by it. Pick a single moment in time and you more often catch the middle of a long event, so unemployment spells come out longer than they really are. If you catch tourists while they're still in the middle of their stay, only the long trips get overrepresented. Cancers found through screening are skewed toward the slow-growing, mild ones. The slower a cancer grows, the longer the window in which screening can catch it, so it gets caught more often, and this is called length bias. The statistic that screen-detected cancers have higher survival is laced with a bias toward mild cancers, and its extreme is overdiagnosis. The National Cancer Institute estimates that about 19% of screen-detected breast cancers and 20 to 50% of prostate cancers stay symptom-free for life. Length bias is a different trap from lead time bias, which only moves the moment of diagnosis earlier. So how do you avoid being fooled? Count completed events as your unit, not snapshots in time, and the bias cleanly dissolves. But not everything is this paradox. The next lane looks faster, is a mix of a structural reason and an optical illusion. In the end, good skepticism is that pause where you ask one more time, is this the inspection paradox too? Now the final twist. The smartphone shakes the whole foundation. All the magic came from a single assumption: passengers arrive at random at any time. Now you check the app, arriving in 3 minutes, and head out just before, breaking your own random arrival. Let's see it in a picture. Same stop with two kinds of passengers overlaid. The orange random passengers scatter even across the long gaps, but the green app passengers cluster only right before a bus arrives. Random gives 9.9 minutes, the paradox intact. An accurate app gives 0.9 minutes. When it misses, 6.1 minutes. The key is the green curve on the right. As more people use it, the wait drops below 5 minutes. When everyone uses it, it falls all the way to 1 minute. The red curve is different. When the bus comes earlier or later than predicted, you're exposed to the long gaps again. Even with everyone using it, the average stalls at 6 minutes, rising above the naive guess of 5 minutes, so the paradox half revives. What dissolves the paradox isn't the app, but accurate information itself. Randomness isn't fate but habit, and information technology is driving the random passenger to extinction. There's one more real-world mechanism that softens the paradox. There's often more than one bus that gets you there. You don't care about the number. You just hop on whichever comes first. When one route falls into a long gap, another route happens to fill that gap. Both Route A and Route B each have their own long gaps where they sit empty for a while. In the bottom row where the two are combined, when it goes empty, B fills in, so the buses come closer together. We raise the number of bunching routes to 1, then 2, then 3. With one route the average is 18 minutes, with two it's 10, and with 3 it drops sharply to 7 minutes. If you have another route to switch to, the power of the inspection paradox is naturally cut in half. Of course, if you stick to just one route, the paradox is still entirely yours to bear. Now at last, let's return to that bus stop and gather today's story into a single sentence. The bus isn't late on purpose, you just land in the long gaps more often. Punctual means you wait half, the more erratic it is, the longer you wait. Today's tools are 2 count events, not moments in time. And look at the variability, not the average. These 2 sentences run like a single thread from buses to cancer screening. Ask from whose viewpoint and by what unit was this average counted? That single question turns your frustration into plain, matter-of-fact arithmetic. It's not your fault. Long gaps are simply easier to land in. If it still bothers you, just open a bus app, or pick a stop with many routes you can switch between. If you enjoyed today's journey, support us with a subscribe and a like. See you at ELLSLAB for the next Odyssey.